In the darkness of the cosmos, where light itself bends and time trembles, lies a phenomenon so extreme that it defies ordinary understanding. Black holes, regions of spacetime where gravity is so intense that nothing, not even photons, can escape, have haunted the imaginations of scientists and storytellers alike. From the first theoretical whispers of a dark star in the 18th century to the modern images of swirling accretion disks captured by the Event Horizon Telescope, these cosmic maelstrom embody the ultimate frontier of physics. The story begins with Sir Isaac Newton, whose law of universal gravitation described how every mass attracts every other. Yet even Newton could not foresee a point where gravity would become infinite. It was the German mathematician Karl Schwarzschild, in 1916, who solved Einstein's newly minted general relativity equations for a spherically symmetric mass, revealing a radius, later named the Schwarzschild radius, beyond which escape becomes impossible. A black hole's defining boundary, the event horizon, is not a physical surface but a point of no return. Cross it, and all paths inexorably lead to the singularity, a point of infinite density where our current laws of physics collapse. Yet, paradoxically, the horizon itself is invisible, it reveals its presence only through its profound influence on surrounding matter and light. Astronomers first inferred the existence of black holes not by seeing them, but by observing the behavior of nearby stars. In the 1960s, the discovery of Cygnus X-1, a powerful X-ray source, provided the first compelling candidate. Matter from a companion star spiraled inward, heating to millions of degrees and emitting X-rays before vanishing beyond an unseen horizon. The classification of black holes follows their mass. Stellar mass black holes, born from the collapse of massive stars, range from a few to tens of solar masses. Intermediate mass black holes, a missing link for decades, occupy the 100 to 100,000 solar mass range, hinted at by dense star clusters. Supermassive black holes, anchoring the centers of galaxies, can exceed billions of solar masses, shaping the evolution of entire galactic structures. Supermassive black holes are not mere cosmic curiosities, they are architects of their host galaxies. Observations reveal a tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of its stars, a relationship known as the M-sigma relation. This suggests a coevolution, where the black hole's energetic outflows regulate star formation, preventing galaxies from becoming overly massive. Active galactic nuclei, or AGN, are the luminous beacons powered by accretion onto supermassive black holes. As gas spirals inward, friction and magnetic forces heat it to extreme temperatures, producing radiation across the electromagnetic spectrum. Quasars, the most radiant AGN, can outshine entire galaxies, serving as cosmic lighthouses visible across billions of light-years. The physics of accretion disks is a theater of extreme phenomena. Viscous forces cause matter to lose angular momentum, spiraling inward while releasing gravitational potential energy. Magnetic fields twist and launch relativistic jets, narrow beams of particles traveling near the speed of light, piercing intergalactic space and depositing energy far beyond the host galaxy. Gravitational waves, ripples in spacetime predicted by Einstein, provide a new window into black holes. In 2015, the LIGO detectors recorded the first direct signal from the merger of two stellar mass black holes, a cataclysmic event that briefly warped the very fabric of the universe. Since then, dozens of mergers have been catalogued, confirming that black holes can and do collide. These mergers raise profound questions about the nature of the singularity. Some theories propose that at the heart of a black hole lies a quantum bridge, a wormhole, connecting distant regions of spacetime. Others suggest a firewall that incinerates any infalling matter, challenging the principle that information cannot be destroyed. The information paradox remains a battleground for theoretical physicists. In 2019, humanity achieved a historic milestone, the Event Horizon Telescope, a planet-wide array of radio dishes, synthesized an Earth-sized telescope capable of resolving structures at the scale of a black hole's shadow. The resulting image of the supermassive black hole in galaxy M87 displayed a bright ring of emission surrounding a dark central silhouette, a visual confirmation of decades of theory. Beyond M87, the same technique captured the shadow of Sagittarius A*, the Milky Way's own central black hole. Unlike its massive counterpart, Sagittarius A** is a quieter, more variable source, demanding sophisticated data processing to extract its faint signal. The image affirmed that even our galactic backyard harbors a monster that shapes the motion of nearby stars. Black holes also serve as laboratories for testing the limits of physics. By tracking the orbits of stars like S2 around Sagittarius A*, astronomers have measured relativistic effects such as gravitational redshift and orbital precession, providing stringent checks on Einstein's theory in the strongest gravitational fields accessible to observation. Looking forward, next-generation observatories promise to deepen our insight. The James Webb Space Telescope will peer into the dusty hearts of distant galaxies, revealing how early supermassive black holes grew in the infant universe. Meanwhile, space-based gravitational wave detectors like LISA will listen to mergers of massive black holes, mapping the cosmic history of these titanic collisions. In the final analysis, black holes are not merely cosmic curiosities to be feared, they are fundamental components of the universe's architecture. Their extreme gravity sculpts galaxies, their mergers echo across spacetime, and their very existence challenges the boundaries of human knowledge. As we continue to explore the abyss, each discovery brings us closer to answering the ultimate question: what lies at the heart of the darkness? Beyond the event horizon, the concept of a singularity teeters between physics and philosophy. In theory, matter collapses into an infinitely dense point where known laws break down, yet quantum mechanics insists that information cannot be destroyed. This paradox drives the quest for a unified theory, compelling scientists to reconcile general relativity with quantum fields, and hinting that the true nature of black holes may be far more intricate than a simple void. One of the most striking confirmations of Einstein's predictions arrived in 2019, when the Event Horizon Telescope captured the first image of a black hole's shadow in galaxy M87. The luminous ring of superheated plasma, warped by extreme gravity, offered a visual fingerprint of the event horizon, turning abstract mathematics into a tangible silhouette against the cosmic backdrop. Yet M87 is just the beginning. In 2022, the same network resolved the shadow of Sagittarius A*, the supermassive black hole at the heart of our Milky Way. Watching the flickering radio waves from its vicinity revealed how matter spirals inward, and how magnetic fields twist and snap, launching powerful jets that can span thousands of light-years. These jets are not mere side effects, they shape entire galaxies. By ejecting energy and matter at near-light speeds, black holes regulate star formation, preventing galaxies from becoming too massive. This feedback loop, observed in distant quasars, shows how the darkest objects can act as cosmic gardeners, pruning and nurturing the universe's grand design. While supermassive black holes dominate the centers of galaxies, stellar mass black holes tell a different story. Formed from the collapse of massive stars, they often exist in binary systems, feeding on companion stars. Their X-ray emissions pulse like a lighthouse, allowing astronomers to map their orbits and weigh them with astonishing precision. When two such stellar black holes spiral together, they generate gravitational waves, ripples in spacetime first detected by LIGO in 2015. Each chirp carries a signature of the masses and spins involved, opening a new auditory window onto the cosmos and confirming that black holes can merge, forming even larger singularities in a cosmic dance. Beyond detection, the aftermath of these mergers poses fresh mysteries. The newly formed black hole often receives a kick, a recoil velocity that can eject it from its host galaxy. Such runaway black holes may wander intergalactic space, invisible yet influencing surrounding matter through their relentless gravity. Finally, the quest to peer inside the event horizon drives bold proposals, from space-based interferometers that could map spacetime curvature, to hypothetical probes riding quantum tunneling shortcuts. Though still speculative, these ideas embody humanity's relentless drive to illuminate the darkness, turning the abyss into a frontier of discovery.